Okay, so there's two things left to do for Prim's algorithm. One is a complexity analysis, and the second is a correctness analysis. So I'm not going to do the complexity analysis here. It's identical to Dijkstra's algorithm, so there's no sense in kind of going over it again. You can find an explanation of it in the book. You can also just replicate Dijkstra's complexity analysis. What I will do, however, is a correctness proof. And so what does correctness mean? Well, we're making the claim that Prim's algorithm solves the MST problem. And so what that means is we're saying that if I ever give Prim's algorithm a graph, what Prim gives me is a minimum spanning tree. And we need to prove that, right? We can't just trust. It's never okay to just trust that a greedy algorithm, any algorithm, but especially a greedy algorithm, is just going to give you the right answer. So let's think about exactly why Prim's algorithm gives us a minimum spanning tree. So let's frame the operation of Prim's algorithm like this. So let's say Prim's algorithm, as it runs, generates a sequence of trees. Okay, so it generates a sequence of trees. T1, or I'll say T0, T1, all the way up to Tn minus 1. Right? Our claim, our hope anyway, is that Tn minus 1 is a minimum spanning tree of the original graph. Okay, so what do we want to show? We just want to show that Tn minus 1, right, the last tree in this sequence, is a minimum spanning tree, MST, of input graph. Okay, so here's one way we can go about this. This doesn't feel like it's enough, but most good proofs don't until you kind of put them all together. So here's the idea we want to show. Let's show that at every step, the tree we have sitting there is a subgraph of some MST. Okay, so here's what we want to do. We want to show for all I in 0 all the way up to n minus 1 that Ti, right, the ith tree, is a subgraph of an MST. And I should say of an MST, right? There could be more than one MST, by the way. And in fact, it's very much worth you going back a video and making sure that you see another MST associated with the graph that we did. Right? There are at least 2 MSTs on the example graph that we did in video 2. Okay, so what we want to show is that each of these trees, as we're building up a tree, is a subgraph of some minimum spanning tree. So this feels like a very weak claim, right? This feels like, if all we have is that it's a subgraph of an MST, how do we know that the last one's an MST? Well, Tn minus 1 is guaranteed to have all n nodes in it, right? Because we know that what Prim is doing is it's adding a node every single time. So if it's a subgraph of an MST and it has n nodes in it, then it's an MST, right? Because we know that every MST has exactly n nodes in it. So that means if it is a subgraph of some MST, it has to itself be an MST, right? It can't have any edges that aren't in the MST that it's a subgraph of, and it has all the edges exactly because it has all the same nodes. Okay, so this is the idea going forward. Is we're going to try to show that at every step, the tree that we have here is a subgraph of an MST, and we're going to use an inductive argument. So anytime you have a proof that you want to make about a sequence, you're going to use induction, right? That's your tool. That's what you have. That's what you have available to you. And so, how does induction work? Well, we have to establish a base case, and then we have to state and prove the induction step. Okay. So, what is our base case? Well, the base case is always going to be the simplest one that feels the most obvious and maybe the most useless, right? So, our base case is the following: T0 is a subgraph of an MST. Is this true? Well, what's T0, right? Let's think about how Prim's algorithm works to understand what T0 is. What we're saying is that each one of these trees has, let's just say it has I edges in it. And so that means it has I minus 1, or that means it has I plus 1 nodes in it. So T0 is just the starting node, right? So it's just a node with no edges. So that's a graph. It's a trivial graph. It's a graph with no edges, right? It's not an interesting graph in any way, but it is a graph, and it is a subgraph of an MST, right? So our first tree is just a node with no edges, so it has to be a subgraph of an MST, right? It's a subset of the nodes and a subset of the edges, trivially in both counts. All right, just a node, so trivially a subgraph of an MST, because we know that an MST has to include all the nodes. Okay, so that is our base case. So the induction step that we want to prove is the following. There's our base case. What is our induction step? So our induction step says, let's trust that everything has worked up to a point, and then just prove that one step beyond that point still works. Okay? So our overall claim here is that Ti is a subset, or is a subgraph of an MST. So our induction step will say, suppose that Ti is a subgraph of an MST, then the next thing Prim does is generates another subgraph of an MST. Okay, so let's write this down like this. If Ti is a subgraph of MST, then what? Then Ti plus 1 is a subgraph of MST. So in induction proofs, this is where people always get tripped up, because it feels like you're trying to prove something with shaky ground underneath it. Okay, but what you can always do is you can say, well, you know, I've got my base case. So suppose I wanted to prove my induction step for step 3, right? For I equals 3. If my induction step is true, then what that means is that I can go from T0 to T1, right, for I equals 0. And then I can use the induction step again and go from T1 to T2. And then I can use the induction step again and go from T2 to T3, right? So by proving the induction step, I actually prove that the statement is true for any index, because I can just reuse this induction step again and again and again. And if you doubt this, you can always go all the way back to the base case and work through one step of the induction step, right? Because you always know, because of the base case, that I equals 0 is true. And so that the if statement here in the induction step is always going to work, right, for I equals 0. And if it works for I equals 0 and you've proved it in a general sense, then it'll work for all the future steps as well. Okay, so what do we have here? Well, Ti plus 1, let's just be very clear about what Ti plus 1 is. Ti plus 1 is the tree that Prim's algorithm gives us in one step if Prim's algorithm starts at Ti, right? So this is Prim's next step after Ti. Right? No, you could initialize Prim anywhere you want to. So if you initialize Prim at some subgraph of an MST, our claim is that the next step Prim does is it will add another node that's part of an MST, right? It will generate another subgraph of an MST. So big picture, if we have both of these, then what we have is a complete proof, right? If we have the base case, which is trivial, we know this already, and we have the induction step, then what we have is a proof that Tn minus 1, right? We can just do this n times, and we get up to n minus 1, and we have that Tn minus 1 is an MST. So let's try to prove this induction step. The base case, we did that already. That's a good base case is one that you don't actually have to think about, right? just is true. So let's do the induction step. So let's let ti be a subgraph of an MST. And what do we want to show? That what Prim's algorithm does is it gives us another subgraph of an MST. All right, so here our simple want to show is that ti plus 1 is a subgraph of an MST. Okay, and so now let's draw a picture. This can be a useful tool to kind of visualize where we are in something like this. So here's our picture. Here's ti. So I'm just gonna draw sort of a hypothetical ti right here. Let's call this graph here ti. And what is our hypothesis here? Our induction hypothesis is that ti is a subgraph of an MST. So let's draw the rest of that MST. Okay, we know that it exists, right? By assumption, ti is a subgraph of an MST. So let's draw the rest of this MST in blue. So the rest of this MST, just for the sake of argument, looks like this. Yeah, that'll be a reasonable way to draw it. And there's an edge here that connects it. Okay, so this whole thing, right? Ti plus the blue stuff. So let's say ti union the blue tree is a minimum spanning tree, right? This is an MST. Okay, so that's our assumption, and I'm just going to name this edge. I'll name this edge E tilde. I had a computer science professor once, actually. One of my very earliest computer science professors was British, and every time he wrote tilde, he called it wiggle. So, you know, I've always, ever since I was a freshman in college, whenever I write E tilde, I think E wiggle. So maybe you'll hear me occasionally say E wiggle, because, you know, it's a real computer scientist said that once to me, so it must be real. So we're going to call this E wiggle, right? This is the edge that connects Ti to the rest of this MST. So here's what we're going to do. We're going to assume for contradiction, right? We're going to generate a contradiction argument here. We're going to assume for contradiction that Prim doesn't do the right thing at this step. Okay, so we're going to assume that Prim doesn't pick that edge as part of its next step, right? Every time Prim adds a node to the tree, it adds an edge along with it. We're going to assume Prim doesn't add that edge. Okay, and what does that mean? Well, it means that it generates a tree that is part of that is a subgraph of no minimum spanning tree. Okay, so here we go. We're going to assume for contradiction. So the way to write this is assume for contradiction. That Prim fails on this step. Okay, that is, Ti plus 1 is a subgraph of no minimum spanning tree. All right, so Ti plus 1 is a subgraph of no MST. Well, if it's a subgraph of no MST, then some edge other than E tilde has to be selected, right? If E tilde were selected, then that would be a subgraph of this blue MST, right? So that means some edge other than E tilde has to be selected. So let's just say, for the sake of argument, that this is the edge that Prim selects. And let me color code this one too. I'm going to color code this one red. Okay, so everything that is our contradiction hypothesis here will be in red. So Ti plus 1 is a subgraph of no MST, and here's our edge that Prim adds. Okay, so what do we know? What do we know about this edge? Well, we know that Prim added it. What does Prim do? It looks at all the edges that are connected to the tree, and it adds the one that has the lowest weight. Okay, so what do we know? I'll try to keep this on the slide as much as possible here. So we know that the weight of EI plus 1, the weight of the edge that Prim added is less than, right, less than the weight of E wiggle. Right? That's just a fact. Okay? Because Prim chose it. We're assuming Prim did something wrong. For Prim to do something, it's Prim's operation is that it picks the lowest edge, the lowest weight edge connected to the tree. Okay, so why do we know this? We know this since Prim selected it. Okay, Prim picked it. Okay, so let's think now about what the next step is. So let's think about what it means for the weight of that edge that Prim added to be less than the weight of E wiggle. And let's think about this blue spanning tree. So we know that the white tree union with the blue tree is a minimum spanning tree. Why do we know this? This was the assumption upon which our entire argument is based. Okay, so we know that all of this, the tree on the left, Ti, union with the blue tree is a minimum spanning tree. So now I want to take that tree and I want to modify it to create another spanning tree that has a lower weight. So here's what I said. I said I want to take a minimum spanning tree and I want to modify it so that it has a lower weight. Okay? That's not a thing that's possible. If it were a minimum spanning tree, then that means there's no modification you can make to it to decrease its weight. Right? So let's go forward then and do this thing that is impossible. And why do we want to do this? Well, we're making a contradiction argument here. Right? We're assuming something that can only lead to nonsense, right? So if it leads to nonsense, to some kind of fundamental contradiction, like a minimum spanning tree is not minimum, then it must have been a false assumption, right? That invalidates the assumption, which would mean that Prim cannot fail on this step, right? Prim must do the right thing on this step. So let's take our tree. So Ti, I'll keep the color coding intact. So Ti union T, and I'm going to modify it, right? So I mean, what do I know about this? I know this is an MST. And so now I want to modify in two ways. First, I want to add edge I plus 1. Add edge E, and I'll color code that one as well. Add edge E I plus 1. And I want to remove edge E wiggle. Edge E wiggle. Okay, so if I add I plus 1 and I remove wiggle, what does this do? Well, this generates another spanning tree, right? So if I go up to this tree up here and I say, now let's get rid of that one and just have this EI plus 1, we know that everything in here is still connected, right? Because it's part of a spanning tree to begin with. And so now we know that what's left over here is a spanning tree. We have a tree on the left, right? This piece here. We have a tree on the right. We have them connected by a single edge, right? So if there's no cycles here and there's no cycles here, there's no cycles in the overall graph after we delete that blue edge, okay? So now red union, blue union red union white is a spanning tree, and it is a spanning tree whose weight is lower than a minimum spanning tree. Okay, so now observe Ti union blue union EI plus 1, and I'm abusing notation a little bit here, saying that I can union an edge into a tree. But the graph that is constructed by taking the white, the blue, and then adding that little red edge there, is a spanning tree. Right? All of this is a spanning tree based on the argument I just made, and its weight is less than that of a minimum spanning tree. less than or equal to TI union blue, okay? The original spanning tree, right? So that is, I've just constructed a spanning tree with a weight less than that of a minimum spanning tree, which is nonsense, right? So i.e. less than the weight of a min weight tree. Okay, this is a contradiction, right? Contradiction. And so let's trace back to when we made our assumption for contradiction. And what was our assumption for contradiction? Well, it was this here in red. And so what does that tell us? That tells us that this thing here that's boxed in red is false, right? This led to a nonsensical conclusion, so it's false. And so now we know that Prim cannot fail on this step. If Prim starts off with a subgraph of a minimum spanning tree, then the next thing it adds just maintains that truth, right? It gives you a subgraph of a minimum spanning tree. And we can track that back and say now we've just proved our induction step, right? So our induction step has just been proved. If we start with a subgraph of an MST, then Prim gives us another subgraph of an MST. There we are. We're done, right? Proof complete.